All right, thank you. Good morning, everyone. Welcome to EML 5215, also known as Analytical Dynamics. This is my name, Riccardo Bevilacqua. I see the writing is good size on the screen. I hope you all can see it this way. So I'm an associate professor in MAE. I'll be your instructor, of course, for this semester. I have the pleasure and honor of being the instructor for this class. So I just opened here my website. I hope you all got a chance to look at the syllabus. It's on my website. It's on Canvas, which I'm still trying to learn, by the way. But I'll try to post things on both sites all the time. So today we're really going to try to break the ice. I need to get used to being filmed. This is my first time. You guys have to get used to at least my accent to begin with. I'm from Italy, and so we'll just get to know each other along the way. Today I will touch on a few topics that will seem to be not very related to each other, but it is just to understand where we are in terms of knowing dynamics. And I really would like to have these lectures to be interactive in the sense that I will solve problems at the board, I will go through theory, but I'll stop often to ask you questions. And you're not going to be on video. Your voice is probably going to be recorded, but no one will know who you are. There is no stupid question except the one you don't ask. We are here to interact. You can tell me whatever you want. Well, almost whatever you want. But there is no stupid answer. Tell me what you think. You can be wrong 100% of the times here. As long as you're fine on the test, you'll be fine, right? So this is really an opportunity for us to learn here in class. For you to learn, for me to learn. I really want you to be involved. And so the first question that I will ask you is, how many have taken a dynamics class before as undergrads? Good, half. Anyone at UF? Another half. So I don't know what your opinion is about dynamics in general, how much you have enjoyed it, but I took it in Italy. I've taken some classes here in the US when I moved. I never really liked dynamics that much. I don't know what you think about it, but it always left me with the feeling that there was someone always smarter than me, able to solve problems with some tricks, some magic, especially complicated problems. I would do fine on sets of problems, subsets of problems, subsets of problems, 2D problems, because they would give me the tools to solve those. But then facing a three-dimensional real problem, I would not be able to do anything in most cases. And then maybe a professor will attack it and solve it in 2 steps, because they would do it by intuition. They have decades of experience. They don't need to go sometimes to the steps, and they can solve the problem. But that was very frustrating. Again, I don't know what your experience has been with dynamics, but that has been my experience. That they would teach me very specific recipes addressing very specific types of problems that they don't extend to the three-dimensional world. If I give you tools that allow you to solve 2D problems, they don't extend to 3D. If I solve problems in 2 dimensions when there is rotation about a single axis, and then you try to extend all that theory to 3D, you have to start all over again, because it doesn't extend. So there is no point in doing dynamics that way. And so what we'll try to do in this class is develop an understanding of basic concepts that will allow you to, in principle, attack any single problem in 3 dimensions, in the actual world we are living in. You're all mechanical/aerospace engineers. If you don't know how to handle dynamics, you're really in bad shape. I don't know if you thought about this, but you're taking aerodynamics classes, you're taking thermodynamics classes, you're taking flight dynamics classes, space flight dynamics classes. The word dynamics is there for a reason, not just because it's cool to have it there. It's because the dynamics is the foundation for what you're studying. So what we do here is what you will need for all of your classes as a mechanical or aerospace engineer. So I'm not claiming that I'm the best instructor in dynamics. I'm just going to claim here that we'll give you a very structured way to address problem with very specific steps, and every single step will be justified, and you will have to understand it so that you can solve problems. And the goal really is understanding those concepts, those tools. There will be very little that you will have to memorize in this class. Very little. I don't want you to memorize almost any formulas. You have to understand the tools and know how to use them. But there's very little memory involved. I'm terrible at memorizing things. Even the cross product with the right-hand rule, I'm not that good at doing that. I have my own tricks to avoid making mistakes, because I don't want to spend brain cells in memorizing things that I don't need to memorize. Understanding is more important. So you will have to bear with me the first weeks. We'll do kinematics for a few weeks, which is the foundation of dynamics. Without the geometry of motion, there is no point in going with F equal ma. Really no point if you don't understand the geometry of motion. So you will see a lot of things that may seem obvious, but again, if you don't know how to do them correctly, every single step, then they're not that obvious. Skipping steps, it's a bad idea. So let me just give you, first of all, a few suggestions on how to approach, from my point of view, the class. Well, the first thing you really need to know is that there is a syllabus, and that's our contract for the semester, right? That's how I call it, actually. So definitely go there. It explains what we're going to do. There is no homeworks here. You're all graduate students. If you're not able to go back to your book and pick problems that you need to solve so that you can get trained, well, then you're not a graduate student. I am doing this job because I like learning. I keep learning. I'm learning from you when I teach. So I'm assuming you're here because you love learning. And so if that's the case, you should be able to, after the lecture, go to the book, read even more than what I tell you at lecture, and try to solve the problems by yourself. So that's the first step. The second one, well, you come at lectures, right? And I'm sure that being an edge class at some point, this number will go down. That's fine. You have the videos. The point of being here is that you can ask questions during the class. And I can ask you questions, and I can make you think, hopefully, with my questions. So there is a benefit in coming here and having some human interaction. But again, there are lectures that will be recorded online, so you can watch those. But then I urge you to take your book, which is the book from Professor Rao, very good friend and colleague of mine in the department, which is a very good book. We'll follow that book and has a bunch of examples and problems. Go watch the lecture, go to the book, study what is in the book, and do solve the problems yourself first. Struggle. You can struggle on one stupid single problem, because nothing is really stupid until you can solve it, for weeks. I don't care. That's how you get trained. You have to suffer. I do it all the time. I suffer on problems for weeks. That's what you do as a graduate student. Okay, so, but if you don't try to solve them yourself, and you watch me solving problems, nothing is going to penetrate. You're not going to learn. You're going to be in front of your test. We have, by the way, 2 exams that you take home. You have 24 hours. It doesn't matter that you can open all your books you want and you have 24 hours. If you don't understand how to solve them because you've trained yourself, you're going to fail. So solve problems here. Really try to do it yourself. And then, I know these are obvious things, right? You should know these things. But I want to put them on video. And then come to office hours. Just come to office hours. I have 3 office hours during the week. The TA, her information is on the syllabus. She has 3 office hours during the week. Come. Don't waste time. Don't wait until the office hours before the test. There's no way you can learn and do fine in a test if you come just at the last minute, okay? They are there for you. So, okay, so doesn't matter if you're taking a dynamics class at this point. You're all in the same shape. Actually, depending on how you've taken dynamics, you may just want to erase everything you think you know, as far as I'm concerned. And we're going to start from scratch. Dynamics is not based on algebra, and is not based on math. That's one thing that I also want to write here. This is a very small board. Try to fit everything. Dynamics is not algebra or math. This goes back to my statement before that most of the cases you're given recipes, formulas that apply to specific problems, and they just come down to writing equations and finding differential equations of motion, and then you look at them and you say, wow, this is really complicated, I have no idea what it is. That's not what we're doing here. Dynamics is based on geometry. What do we do in dynamics? We look at the world we're living in. In this class in particular, we'll look at particles, systems of particles, and rigid bodies. And we try to describe how they move and explain why they move that way. And I would add, we also try to predict how they behave in time. That's what we do in orbital mechanics. We have orbital propagators that tell us where a satellite will be in 1 or 2 days. They are based on the equations of motion. So that's what we want to do. Now, what is this world we are living in? How do we describe this three-dimensional space we're moving in? Mathematically speaking, what do we call this? Or geometrically speaking, I should say. This is the point where you can say whatever you think is right, and it doesn't matter.
Euclidean space?
Euclidean space. All right, so we live in, I would add, three-dimensional, let me write 3D, Euclidean space. And it's not our focus describing what this means, but this 3D Euclidean space comes with very specific definitions and properties that try to resemble the world we're living in. One of them is the definition of measure, of distance between points, right? And this space we're living in is geometrical. If I want to define what is the distance between my eyes and these sunglasses down here, I cannot state that it's 3. It's not because I'm not adding the units of measurements. I have to tell you a direction. I have to tell you where the origin is, where I'm measuring from, and in which direction in 3D space. So it's geometric, right? In dynamics, we're going to talk in terms of vectors, right? So I'll ask you this question. What do you call this? You will call this a vector, right? Well, you sure this is a vector? I see 3 numbers. I mean, MATLAB would call this a vector probably, but that's an abuse. This is 3 numbers. I mean, I just put the brackets around them, but if you don't give me the basis, this is just 3 numbers. This is not a vector. This is not a vector. So again, today I'm not trying to look smart and confuse you here, but I'm just trying to point out that we use everyday terms that we don't completely understand. We use objects that we don't know how to define correctly, or at least we've grown used to use them, but sometimes we abuse terminology, sometimes we solve problems, but we don't really know exactly what it is that we're using. A vector is this. This is a vector, 3D Euclidean space. This is 3D Euclidean space. This is a vector. It's a quantity with what? What are the properties of a vector? Magnitude and direction. Okay? That could be the representation of a vector in a specific basis that I haven't given you. So if I give you 3 numbers, if someone gives you 3 numbers and they tell you this is a vector, tell them, no, this is not a vector, these are 3 numbers. You haven't given me the basis. Because the basis for this could be 3 orthonormal vectors, which we usually use, or it can be just 3 skewed directions at weird angles. It could be anything, right? So that's definitely not a vector. So let's start with a few definitions here, just to warm up, I guess. So we just said what a vector is. A vector, let's call it B, is, you said that, it's a quantity in, let's call it E3, which is my 3D Euclidean space. We just call it E3. Which possesses both magnitude and direction. And I'll have to go over. OK. In this class, there's nothing we say or use that doesn't have a clear definition and that we completely understand. Well, we understand E3 Euclidean space, I hope. What is magnitude and direction? I need to define them. Intuitively speaking, I see these arrows. We represent vectors with arrows that has a certain length, right? And it's pointing in a certain direction. But what is the formal definition? 3D Euclidean space comes with some properties, as we said, right? Well, magnitude is defined as, since we have a way to define distances and lengths in 3D Euclidean space, it is defined as the square root of b dotted with b, where this symbol here, the dot, is also called the inner product in E3. And then direction, on the other side, usually we define direction as the unit vector that corresponds to b, right? So we say direction is, let's call it ub, is b over its magnitude. And you can prove that this is really of magnitude 1. This is a vector. Now, if you project it in a basis, then you can associate 3 numbers with that vector. But that's a representation of a vector, right? Vectors exist in 3D Euclidean space no matter what you do. No matter if you're sleeping, you're awake, you're looking at them from this point, from this other point, doesn't change the fact this vector exists and it's right here. So the way you represent it doesn't matter. It's completely coordinate free, point of view free. It does exist. It's there, right? If I grab a pen, I don't have a pen, call it pen, I call it penna as I would do in Italian or any other language, doesn't change the fact that this is something used to write. It doesn't change its essence, right? So there are 2 different things, objects that we use that exist and the way we represent them. So 3 numbers are a representation of a vector, maybe, if you give me a basis. And so one thing I forgot to tell you, these are my cheat sheets. I'm not going to share these with you because they may be in Italian, first of all. And I don't like losing things along the way, so these are just my ways to remember what I have to tell you. There is really no point in sharing this with you. I don't advise we do that. So representation occurs in coordinate frames. Coordinate systems. That's the first mistake that we all do all the time. What is the difference between a coordinate system and a reference frame? I had no idea until I was a graduate student. Well into grad school, I thought they were the same thing.
Coordinate system is a fixed in a reference frame?
Yes. What is the definition of reference frame? Again, today we're just randomly touching on these things, just to understand that they have clear definitions and that we're going to stick with them for the entire class. And as we solve problems, we're going to define reference frames and coordinate systems every single time. What is a reference frame? Can you guess? Just in words, what do you think is a reference frame? How many are thinking in their minds directions, axis? How many are thinking this? Something like this, right? I always thought this for a long time. This is not a reference frame. This may be a coordinate system, but let me erase this. Reference frame is this table. It's the board is the floor, it's your table. It's a perspective from which we see things happening, from which we observe the world around us. What happens in 3D Euclidean space? What is the most common reference frame that we use all the time?
Our perspective.
Yes. What about this planet? Earth is the most common reference frame. Unless you're flying on the space shuttle or you're on an airplane, most of the experiments and observations we make, we're stuck to this planet. We're right here, right? We look at things from this point of view. And unfortunately, that's not usually very convenient. If, as we do in my field, we design missions that go to another planet, well then, you don't really care about what the spacecraft is doing with respect to you down here. At some point, you probably want to know what the spacecraft is doing with respect to other objects, other bodies, maybe the sun. But you can't be on the sun, right? Well, this is one of the first things we'll see, again, not today, but we'll see that there is a way that allows us to relate reference frames to each other. If I can look at something from here, from this point of view, I can tell you how another observer on another reference frame, on another body, or on the sun, would see the same phenomena occurring, as long as I know how the Earth and sun move with respect to each other. I'm going ahead of myself here, but there are substantial differences between coordinate systems and reference frames. So let me start with coordinate systems. When I said before, we have three, and we're going to redefine these things more formally starting next time. Again, here, we're just having a conversation. Let's say that we have three linearly. By the way, if my writing is not clear, this is the time to speak. Okay? Independent. Vectors. Well, it should be clear that from now on we're going to be in E3. And let B written in the following way, B1 E1 plus B2 E2 plus B3 E3. Let that expression be the representation of B in E1, E2, E3. Oops. What do you call E1, E2, E3? What would you call that? That's a basis for E3, right? As long as they are linearly independent, this is a basis for E3. These three vectors can be anything. E1 this way, E2 this other way. The angle between them can be any number. And as long as E3 doesn't belong to the plane of the board, assuming that E1 and E2 are on the plane of the board, we're fine. They are linearly independent. I cannot express E3 as a combination of E1 and E2, right? If they are not in the same plane. So these angles can be anything. But usually, we like to use bases that are convenient. What do we do with them? We pick one that the vectors are mutually orthogonal. How do you write that down? Other than in English, using the vectors.
Dot product is 0.
Okay. Dotted with EJ is 0 for I not equal to j. We want them to be unit vectors because it's more convenient. Can you imagine if these three vectors were different magnitudes? B1, B2, B3 will be all over the place. It is possible, you can do it. We just don't do it because it makes the math so hard. So this means that the magnitude of any of those EY is equal to 1 for I equal to 1, 2, and 3. And there is one more thing that we do when we define a basis. They are perpendicular, unique length. What do we do? What else? Is that it? Is this okay as a basis? Do we use this? This is my left hand, by the way.
Must be right.
Right-handed. Right-handed, right? Now this, what is this doing for us? Why do I do what do I need to do this? Because if you pick E1 and E2, and they are at 90 degrees, then you can have two different directions for E3, right? So there is ambiguity here. So someone a long time ago said, let's do right-handed rule. Now this gives me an excuse to show you how bad I am at memorizing things, and I don't want you to memorize things that are not necessary except concepts. Those you don't need to memorize, you need to understand. You can do the right-hand rule, or you can do something else, which is also described in your book. Very little trick that I will actually use in solving problems because I don't want to think about cross products. That's an operation that shouldn't be an issue. It shouldn't interfere with my thinking about the actual problem I'm trying to solve here. So I'll do this diagram. This is one way of doing cross product that allows you to avoid mistakes. Put the vector in the order you want to define them, clockwise, arrows the same way. If you're doing cross products this way, you get pluses. If you do it the other way, you get minus. E1 cross with E2 is plus E3. E3 cross with E1 is E2. E1 cross with E3, now I'm going the other way, is minus E2 and et cetera, et cetera. Nothing special. I use it. I don't want to memorize things. I don't want to do right-hand rule. I don't like it. So you find your own way to save brain cells for more important things. That's my comment. Now, so when I shouldn't have erased this, B is B1, E1, plus B2, E2, plus B3, E3. This is the representation of B. This is not B. This is just one way of calling B in some basis. You change the basis, you get three different numbers. Don't confuse an object with its representation. That's my point. You definitely don't want to do that. So, talked about that. Now, why am I bothering about talking about vectors and coordinate systems? And we haven't touched on reference frames yet. Well, in dynamics, as I said, we're going to look at the motion of objects in 3D Euclidean space. And so, if we are in real 3D Euclidean space and not in some weird b-dimensional space that it's easier for us to deal with because we know how to solve problems there, which it's undergrad dynamics, well, we're going to deal with positions, velocities, accelerations, angular velocities, and I would add also forces at some point. It will be sometimes before we get to forces and torques. But we'll have to manipulate these objects. What are these? They're all vectors, right? They're all vectors. Now, there is something about these two in particular, to start with, that is a little tricky, right? Positions where you decide where your origin is, you define your basis, and so you can define the position of a point with respect to another point. You need to have an origin to measure the position of. a particle, for example. But these two in particular, they change quite a bit depending on what. If I'm standing right here in front of you, I have what velocity? 0, no velocity. If I walk, you see me moving, my position is changing with time. So there is a non-zero rate of change of my position. If you walk side by side me, you don't see that anymore. If you're on the highway, you are on I-75, you're going 70 miles an hour, you're going to Disney World, and you have a guy that is driving next to you at the same speed, which is, by the way, extremely dangerous, but that's what people do all the time. So same speed, 70 miles an hour, do you see a rate of change of his position with respect to you? No. So this, with respect to, it's very critical. Velocities and accelerations, and I'm not going to write them down for now, they are rates of change of position. Acceleration is a rate of change of velocity. They depend on who is looking at the phenomena that it's occurring. They are reference frame independent. So if I take the rate of change of this vector, and this vector is doing this, I do see it changing. But if I go with the vector, I don't see it changing. So it really depends on your point of view, your perspective. So reference frame, someone said a reference frame, a coordinate system is fixed in a reference frame. Reference frames are points of view. The Earth is one potential reference frame, and this is our point of view when we look at satellites and other things going on. And we're stuck with this reference frame, and we cannot look at things from any other reference frame usually. Okay? So let's try to formalize what a reference frame is. I said it can be a table, it can be this board, it can be the floor. Let's start with some definition that is not extremely formal, and then we'll actually give it a description in E3. We're moving in E3. Everything we define and use is in E3. Is based on points in 3D Euclidean space. So we can start saying the reference frame is a perspective and I always go above the line from which motion is observed. Now, if I am an observer in this reference frame, I need to be fixed in this reference frame. If I am looking at something happening and I am in the Earth's reference frame, I better not be walking. If I'm looking at something going on the table, an experiment, I don't think it's a good idea to keep doing this, right? I'll be crazy, taking measurements of something as you move back and forth. Pick your reference frame and stay attached to your reference frame. So let me add the sentence here. An observer in a reference frame must be fixed in that frame. If my reference frame is the board, I glue myself to the board to see things as an observer in that reference frame. I glue myself to the table. I don't move with respect to the Earth. That's how we're going to approach problems. When we define an observer that is looking at positions of particles, for example, we're going to state exactly in which frame that observer is fixed. Now, this doesn't tell me anything. I am in E3. It doesn't really give me a definition of a reference frame. It's intuitive, but again, I said at the beginning that I really don't want you to leave this class thinking that you can solve problems just by intuition. Maybe you get there at some point. I am yet to get there. If I try to do things by intuition, I usually make mistakes. So I apply the concepts that I understand and I know in a systematic way. And again, this is not a good way. I mean, it's a way to define a reference frame, but it's not a formal way to define a reference frame. we are in E3, and so to define a reference frame, I probably need 3 points. 3D space, I need 3 points. So let's give the formal definition, which is the following. Reference frame is any set of at least 3 non-collinear points whose mutual distances instances, let me go down here, are constant. Here is your reference frame. 3 points, not in line, that's a reference frame. It can move in 3D Euclidean space. I can take this board and move it around. That's a reference frame, as long as the mutual distances don't change. What if I defined also this way? You've taken some dynamics here and there. So which objects have this property that the mutual distances don't change with time and they have at least 3 points? Rigid bodies. So a reference frame is a rigid body. So when we'll do kinematics of reference frames, we'll do kinematics of rigid bodies. It's the same thing. That's why I said that these can be a reference frame. It's pretty rigid. This is also a reference frame. The Earth, well, I doubt that all the points remain a constant distance, but we usually use it as a reference frame. We make a lot of assumptions in dynamics that usually we don't know. When you write, and I don't want you to write this down, F, it will take a while before we get here. F equal ma. We write these all the time. Where is this valid? This is valid in an inertial reference frame. And I don't want to even describe what inertial is, because reference frame is something that you need to describe first. If you don't know what reference frame is, what's the point of describing an inertial reference frame? So I need to know exactly what is the definition of every single object that I use in my problems and where those objects are described. So what I was going to tell you. Reference frames, as I said, it could be the Earth, it could be the Sun. Most of the times you're measuring things from the Earth. And most of the times what you measure from the Earth is not what you want, because you may want things to be represented with respect to the Sun. Well, there are ways to relate to each other, these frames. And that's called transport theorem. We'll get there in a couple of lectures. That's an extremely powerful tool. It's unbelievable. You can tell what an observer on the Sun would see, an alien on the Sun would see, if you know how the Sun is moving with respect to this planet. You don't need to be there. You can look at your satellite flying over you. You take its position and velocity and acceleration. You can tell what is the position, acceleration, and velocity of that same object with respect to the Sun. That's how we solve problems in dynamics all the time. Otherwise, we'll be in huge trouble. Now, going back to one of your statements before, coordinate systems are fixed in a reference frame. So the first thing that you will have to do, and we'll see this formally, solving problems, is first of all define your reference frame, your perspective. If you're looking at this world and things are moving in 3D Euclidean space, well, first of all, you have to tell me from which point of view you're looking at things, right? That's the first thing you have to do. So you first define your reference frame. You tell me what that is. But then, by itself, does it tell me anything? If I want to then quantify the motion that I'm observing, they don't give me any tools. I mean, I can glue myself to the board and I look at you guys moving back and forth. I can qualitatively say that you're going that way or that way, but I'm not measuring anything. The measurement is what the coordinate system allows you to do. So this is my board reference frame. These are my 3 points. Now I can build a coordinate system. For example, I pick E1 to be along the direction of 1, 2. and then some intermediate E2 prime along the direction of 1, 3, I do the cross product between the two, and I get something which is, well, let's put this in perspective. It should come out of the board, right? E3 would come out here, and then according to my right-hand rule or the diagram that I showed you before, I define E2 right here. So once you give me 3 points, at least 3 points, I can build a coordinate system. But that's not the only way, right? But once you build it, that coordinate system must be fixed in the reference frame. It cannot move. If this reference frame starts rotating and moving, these unit vectors go with the reference frame. E1 remains aligned with 1, 2. Same goes for E2 prime, E3, and E2. They go together. A coordinate system is your ruler, is how you measure things. You can quantify things with a coordinate system. So you wouldn't want to move your ruler when you're taking measurements, right? So what is true is that a coordinate system is fixed, must be fixed in a reference frame. A coordinate system must be, I will say more, must be fixed with only one reference frame. Right? On the other hand, you can have infinite reference coordinate systems fixed in a reference frame. The Earth is huge. You can put your origin of your coordinate system here and define 3 axes, and then you go to the equator and you have a different coordinate system. Then you go to the North Pole and you have another coordinate system. As long as you define them and you glue them to the reference frame, they don't change. Those are your rulers. You can measure things that way. So before we conclude today, there are very important ingredients here that we're going to use. We're moving in this space. We are going to use vectors for every single problem that we solve. It doesn't matter if it's planar, if it's a linear motion. We'll set it up in a way that uses vectors, because that's the only way to do dynamics. It doesn't matter if your problem is just along a line and it's very simple. Good for you. You're lucky. But then if you do go to 3D, you need to use vectors. So that's what we'll do. Every time we'll approach a problem, we'll define reference frames. And after we define the reference frame, all the reference frames that we need, we will attach coordinate systems to them. What I said at the beginning, this is a course that uses geometry. And we'll use some algebra, right? But this comes first. You first define, and down here we see reference frames that allow us to formulate problems. When I give you a diagram of system of particles moving with respect to each other, if I give you that, and I ask you to compute the acceleration of a point in that system, and that's it. I just give you the drawing, as we'll do. You need to formulate the problem first. I'm not going to give you what the reference frames are. You decide. You decide all these things. 5 minutes. So this is the part on which we're going to focus a lot for every single problem. The formulation of the problem is the most important part. Then once you have defined your coordinate the reference frames, then you can go and implement the problem. You can have coordinate systems and start doing your calculations. So here we really have the implementation of the problem. One thing is formulating the problem, writing down the problem, and one thing is going to MATLAB and actually coding the problem and solving it. I'm assuming that all of you know how to do algebra and math. This is not a class about that. I don't care about this as much as I care about this. So when you start solving a problem, you don't skip any steps. As we'll see it. We'll start doing some problems pretty soon. If you skip steps, or if you kind of guess on those steps, that's when the problem comes. If you do this part right, you set the problem right, you show me that you understand what reference frame is, coordinate systems are fixed to reference frames, etc. And then you mess up on your calculations, you confuse a minus with a plus. Well, yeah, you may lose some points, but not as much as here. If you're guessing on the concepts, well, then that's a 0, okay? So that's what we're going to see from next time. We're going to redefine these things a little more formally, and we'll start seeing how, given two different reference frames, how the rate of change of vectors relate to each other as seen from different reference frames. Okay? Any questions for today? Are we confused enough? Not yet? Good. Thanks.